So this is a problem from the 2007 AB Calc exam. It was on Form B. It's a calculator question, and the situation that you're presented with here reads that an object is moving along the x-axis. Its velocity is given by this function. They've provided us with a graph of the function, and it holds from 0 to square root of 5 pi. They tell us the position of the particle is represented by a function x of t. And at time t equals 0, the position, so at t equals 0, the x value is equal to 5. In part A, it wants us to find the acceleration of the particle at time t equals 3. Well, if the calculator's in play, the easiest thing to do here would be to graph this velocity function on the calculator, because the acceleration at 3 is going to correspond to the velocity evaluated at 3. And although the calculator can't find you the acceleration function, the calculator can find you the value of the derivative of this graph at 3. And in this case, that's exactly what we want to find. So if we go into the calculate menu, we can grab this dy dx feature, the value of the derivative. We want the derivative of what we graphed evaluated at 3. So we'll type that in. Calculator gives us the answer. We're looking at an acceleration of negative 5.467. Doesn't really give us any units here, but that would be maybe meters per second squared, if that's what velocity was measured in, meters per second. Easy to do this with the calculator. If all you need is a single value of the derivative of something, you can find the derivative just like we just did. Now in part B, it wants us to find the total distance traveled on the interval from 0 to 3. Now, if we think about the units of velocity, the units of velocity are going to be meters per second, miles per hour, units of distance over units of time. If we multiply by something that has units of time, the units of time are going to cancel out, and we're going to have a result that's measured in miles, in meters. So in our integral, if we have meters per second times the dt, which would be measured in seconds, the same way that t is measured, we would have a result that's just represented in meters. Now, if we want total distance on the interval from 0 to 3, we're going to have to integrate velocity on the interval from 0 to 3. The only hang up here is this integral here is going to compute all of this area and give it back as a positive since it's above the x-axis. This area is going to get computed by the definite integral as negative since it's below the x-axis, and then 3 is actually about right here on the axis, and all of this area is back above the x-axis, so that's going to come back to us as a positive. If we're looking for total distance, we don't want to subtract anything off of that. We just want to keep accumulating and adding it all up. The easiest way to kind of make the adjustment here, and if the calculator's in play again, this is very simple to do. All we have to do is hang some absolute values here, and what that's going to cause to have happen is all of these negative y values, all of these velocity values that sit below the x-axis, if we take the absolute value of them, they're flipped back up above the x-axis or the t-axis. So I want to actually graph this function here. The absolute value, be out of the math menu, absolute value of v of t, so the absolute value of sine of t squared or sine of x squared. And what you should see happen, you should see the same shape. This piece of the graph isn't affected, this piece isn't affected, this piece isn't affected, but all of these portions that were negative, these two pieces sitting down here, they're reflected up above the x-axis because of those absolute values. Now if we do this integral from 0 to 3, and we can do this on the calculator, do this integral from 0 to 3, all of the region is above the x-axis, all of the area is going to be summed, nothing is sitting below the x-axis and going to be subtracted off, and so our final answer for this would be about 1.705. And again, there aren't any units specified here, but it'd be meters, miles, depending on what the units of velocity were. In part C, they want us to find the position of the particle at time t equals 3. Now, position would be measured in meters from the origin, miles from the origin, whatever the units of distance in this case are. If we do the integral of velocity, we get something that has units of meters, miles, depending on what the units of velocity are. We want to figure out what the position is at t equals 3. This alone will not determine that, because all this is going to do is going to figure out how far the object moved forward on the interval from 0 to this t value, figure out how far the object moved backwards on this interval, and then figure out how far the object moved forward the rest of the way to 3. We have never taken into account the starting position. This is just going to represent displacement. You integrate the rate of change of position, which velocity is, you get how much position changes from 0 to 3. You want the final position, you're going to have to figure out what the initial position was. Well, they gave it to us in this case, and then add on the change in position from 0 to 3 to determine that result. I did the last integral on the graph screen. I'm going to do this integral from the home screen just because this is an option we haven't really done quite as much, and it's a little nicer when you're adding something to your integral to go from the home screen. So I'm going to do 5 plus that integral. To do an integral from the home screen, I'm going into the math menu, and at the bottom of this list there's a function integration feature. And we want to type in the function that we're going to integrate. So the function we want to integrate is sine of t squared, or sine of x squared. So here is the function we want to integrate. I next need a comma. Now I'm going to specify the variable of integration. Well, the variable I gave the calculator there was x. Another comma. Then you're going to give the calculator the lower limit of integration. Another comma. Then you're going to give the calculator the upper limit of integration. And when I hit enter, the calculator is going to do this calculation for me without having to do it from the graph screen and then bring it back and add 5 to it. So we end up with a final position of 5.774 meters, miles from the origin at time t equals 3. And in the last piece of this, what the problem asks us to do is figure out where on this interval the object is farthest to the right. Now if you think about being farthest to the right, if the object is moving back and forth on the x-axis, we're basically asked to find the maximum position, the absolute maximum value of the position function, x of t. We can do this without actually finding x of t. We have enough information provided to us in order to allow us to determine what the maximum of x of t is. And if you think about how you would normally do this, you would take the derivative of x of t and you'd set it equal to 0 to find what your critical numbers are. Well, the derivative of x of t is actually what we're given. They've given us the derivative of x of t. We would want to know when that is 0. Well, it's 0 at these locations on the t-axis. I'm going to take a minute to find those on the calculator real fast, and I'll just label them on my graph, and we'll get back together in a minute to talk about the conclusion. So I did take a minute to find all the critical numbers of the function x of t. The derivative, the velocity function, is equal to 0 at these 4 times on the interval from 0 to square root of 5 pi. Our candidates are also going to include these endpoints. Okay, so we basically have 4 locations where the absolute maximum value of x of t can occur at the endpoints of the interval and at any of these critical numbers between those endpoints. If you think about what the sign chart for the function x of t would look like, or x prime of t, excuse me, what the velocity sign chart would look like, you know, we would have split values on it at 1.77. We'd have another split value at 2.5. We'd have another split value at 3.07, and the last one at 3.5. And then here we'd have 0, and then here we'd have the square root of 5 pi. The velocity is positive on that interval. The velocity is negative here. The velocity is positive between these 2 values. The velocity is back to negative between 3.0 and 3.5, and then the velocity is back to positive for the remainder of the interval. We can eliminate a lot of our candidates because an absolute maximum cannot occur at a local minimum. Our position is increasing, decreasing, increasing, decreasing, and then increasing. We don't have to worry about 3.5. That's going to be a local minimum. Right? The local minimum has no chance of being the absolute maximum. Same thing about this one. Now, these are local maxes. 1.7 is a local max, 3.0 is a local max. So the maximum could potentially happen at those values. So basically what I want to know is I want to know the position of the particle at 0, beginning of the time frame. We know that. That's given to us. That's 5. We want to know the position of the particle at 1.772. We want to know the position of the particle at 3.070. And we want to know the position of the particle at square root of 5 pi. What we have right now is we have 3 more problems, a lot like what we did in part C. If we want to know the position of the particle at those times, we're going to have to do these integrals, 5 plus the integral from 0 to wherever we want to end our interval. So if we think about how the calculator can help us here, we can go back and basically just reuse this expression here. We want to do the calculation from part C for the interval from 0 up to 1.772. So I'm just going to reevaluate that same expression. So second entry, I want to evaluate it on the interval from 0 to 1.772. And that's going to give me a position at that time of about 5.895. I want to figure out what my position is at 3.070. So I'm just going to evaluate this again. And that would give us about 5.788. And then I want to know the position at the square root of 5 pi. So we're going to evaluate this one more time. So second enter. And we'll change that upper limit of integration to the square root of 5 pi. And I guess I do need one more parenthesis to close that. I don't know why I hit that button. That's what I wanted to hit. And I end up with 5.752. So where's the maximum position? Well, the maximum position happens at the t-value of 1.772. Why? Well, we figured out what the candidates were. We eliminated the local mins, and we determined that this was the maximum value of the position function.